Howdy, my name is Dr. Brent Garrett Vella, and today we're going to go over the first law of thermodynamics, some of the practice problems that we had at the end of the lecture. So we will get started with problem 1. This was heating at constant volume. So the problem says that we have 1 mole we have volumetric heat capacity. This is something that you'll need to memorize. We have the initial temperature. We have the final temperature. And for niceness, we can say the final temperature is equal to 2 times T1. Okay? And then we're heating at constant volume, it says. So volume 1 is equal to volume 2. Let's draw the PV diagram. Let me see if I can do a straight line here. Not bad. V, P, this is P. And what we will do is we will go from V1 to V2 How do I know pressure is going up? So volume didn't change, so delta V is 0. How do I know that the pressure increased, right? Just think about it. I start at a low temperature, so here I'm saying I am at T1, comma, and then here I go up to T2, okay? Remember on the PV diagram, this is something good to keep in mind in general. Let's see what this looks like. This is not exact. Yellow isn't good. Let's try white. Yeah. There are these temperature gradients, okay? So this is T high, T low. So this is something that you should think about on any ideal gas, right? When you draw P and V, there's also temperature. Temperature also is accounted for, but it's in plane. So if we were to plot this in matplotlib like we usually do, you would see this as the color axis, okay? So I know that if I'm heating up, right, if I'm increasing the temperature, pressure will also increase, right? That's your PV is equal to nRT, right? Okay, so that's great. We know that, let's see what we were asked for. One of the questions was work. That's something we can answer pretty quickly. Work is equal to P dV. Work is equal to the integral from V1 to V2 of pressure with respect to volume, okay? The area basically under the PV curve. That's nice, okay? So work is equal to 0. Then what else can we do? If work is equal to 0, according to the first law, we have Q minus W, work is equal to 0. So we know the change in internal energy will be equal to the heat transferred, okay, Q. Now, what can we do next? We have an ideal gas. So there's one more thing that we can use. Because we have an ideal gas and we have temperature change, which is here, what we can say is du is somehow proportional to the temperature change, right? This is, and it's only proportional to the temperature change. This is for an ideal gas. Right? How is it proportional? It's proportional like this. du is equal to n CV dt. This is the proportionality constant, right? So n is equal to 1. We have, let's work over here. We have CV. We know R. Okay. We know delta T. We know R. We know this. Therefore, we can get U. U, in this case, let me see if I have it written out. If you would do the math, it is 3.74 kilojoules. Right? So we have that as well. And we know that U is equal to Q. Ooh. Let's just say Q is also equal to 3.74 kilojoules. Okay? What does that correspond to? So what does this mean? It means that we had this vessel. We had this vessel. And we added heat to it. Let's see if I could do a different color, just for aesthetic. All right, so heat went in. No work happened here. If heat went in, the internal energy increased, so temperature went up, right? So we can call this the pressure cooker scenario, right? Just to put an image to it, okay? So the volume can't expand, we added heat, pressure builds and builds and builds, okay? And temperature increases. So that's example 1. Give me a little bit of time to erase this, and we'll be back. Okay, we will do 2, constant pressure heating. So let's see what the scenario was here. We had 1 mole. Initial temperature was 300 Kelvin. The second temperature was 600 Kelvin. And again, for niceness, we can write 2 times T1. We have these hold true for our ideal gas in this situation. Again, you need to remember these and when to use them. Okay. We are told that pressure is held constant. We have an initial and final temperature. And we have these heat capacities, right? Let's draw the PV diagram first. Let me try to do this. Okay. I could maybe... There you go. So here's P. There's V. And then we are told that we are going from P1 to P2. But P is constant, right? So that's why we have this here. That means there is a V1 and V2, right? And what are we asked? We're asked for Q, enthalpy, internal energy change, enthalpy change, I should say that. And yes, okay, so let's get started. Also recall, before we get started, also remember though, it's good to keep in mind that there's always temperature gradient. So there are isotherms on this. So that means T high, T low, right? Roughly. We know that temperature should increase then. We know, actually, one thing, we know temperature increases, right? So we know that this is higher, and we know that this is lower, right? So I could even say that this isotherm right here, just extra, this isotherm is the 600K, this isotherm is the 300K, right? Qualitatively. Okay, now we can get started. Let's start with the first law. du is equal to Q, heat added, minus work done, right, by the system, okay? So we know that there's expansion here, right, because we have volume 1 to volume 2. This means that we know we have a work term, right? So we know we'll have a work term. What's another thing that we know? We know that we have, yes, we can do, we have an ideal gas, and we know CV, and we know delta T. So we can say, we know temperature and the change in internal energy are proportional. How are they proportional? They're proportional by this constant here, or not constant, number of moles, and this constant, which is the heat capacity. So then that ends up being, moles is 1, let's just do that. And then CV is 5 over 2R. And then we know that it is 600K minus 300K. If you wanted to put it nicely in symbols, you could just say T1 because we know, right? Okay, so 300K. And when we do this math, we will see that internal energy will be equal to this number, 6.24 kilojoules. Okay? Question. We have a process where we are expanding, right? We're going from V1 to V2. Is it okay that I use the constant V heat capacity here? Because V is not constant. Yes. So that was something that used to trip me up as a student. This holds true for ideal gas. It doesn't matter the process, right? As long as you have this delta T and you know you're dealing with the ideal gas and you know that the ideal gas has the volumetric heat capacity 5 divided by 2R, right? that is how you get U, okay? It doesn't matter the process for this equation, right? Because for an ideal gas, U, remember this, for an ideal gas, U is only dependent on T. Okay. So we have constant pressure. That should also set up alarm bells too. The in a constant pressure process, this holds, okay? So we know that the enthalpy change will be equal to the heat in or out of the system, okay? That's constant pressure. That's why we kind of like enthalpy. Well, how do we get enthalpy, right? So if we look here, we know U. We know there's a work term. We don't know it yet. We don't know Q. But we know Q is equal to the change in enthalpy. But again, for an ideal gas, what you can say is enthalpy is equal to this, right? You can always say that. This gets into the definition of what heat capacity is. This was derived in the lecture. Okay. So what we can do is we know moles is equal to 1. We have this, which is 7/2R times 600K minus 300. Oop. A little off the screen. This is 300K difference, okay? So when we do the math, we will get that this is equal to 8.73 kilojoules, right, for 1 mole. Okay, so we know delta enthalpy, the change in enthalpy, and we know that that's going to be Q as well. So let's write, we know Q as well. And then all we need to do is get work, this integral term, okay? What we can do for that is just rearrange. We can say delta U minus Q, or you could also say delta H, right, these are the same, is equal to minus work. What you can then do is just flip these around. Or you can call this Q. I'm switching these out. There, Q and delta H are the same. Right, I just wanted to get rid of the negative on the work, right? So then I have 8.73. Where did I write it down? 6.24 kilojoules. So the units are for both. And that means work, can't really see it. Let me put it up here. Can't see that either. I'm going to put it here for our final answer. Work is the difference between those two. I have it written down. Is equal to 2.49 kilojoules. Okay, so the work done by the system is 2.49 kilojoules. Okay, so now we can do our retrospective again. What was happening here? We have our vessel. And it'll be like a piston. Okay. right? And this is where we were. Right, in the gas. So this was the initial state with volume 1 and a P1, right, the density of these, the frequency that they were hitting the wall. And then we add heat. So here's the heat. So basically I'm saying Q goes in. This expands, but it has to expand in a way that keeps the same pressure. So we're holding pressure constant. I shouldn't have made it so dense because I'm going to have to do a lot of points here. Actually, I'm not adding any. Let's see. But pressure is held constant, okay? The density doesn't change. We're not doing chemical potential. Okay. To V2. It had to increase temperature to maintain the pressure, and it also expanded. If it expanded, there's some work done, right? So this is a piston moving, essentially. You can call this a piston moving. Piston moving by heat. Constant pressure. So that's the scenario. Give me a moment. I'll erase this and we'll move to the next one. So in this problem, we have isothermal reversible expansion. Okay? So we were told in the problem statement again, let me make this. We have 1 mole. T is equal to 300 K. This is isothermal, so T1 and T2 are equal to 300 Kelvin. It's expansion, so isothermal expansion, so we have 2 volumes. 1 liter, and V2 is equal to 5 liter, and to put it nicely, we could say 5 times V1. Okay, if we wanted to solve symbolically. Let's draw the PV diagram. Okay, and remember, the PV diagram has isotherms, okay? So isotherms qualitatively look like this for an ideal gas. And what's nice, in this example, for isothermal expansion, they both lie on the same isotherm. This is the 300 K isotherm, okay? Other isotherms exist. And they look something like this, right? I'm not doing it exactly, but this is a higher temp. This is a lower temp, okay? Just remember that. Let's take a quick break and say, why is that the case? Why do you think that's the case? Right? So let's just start here at any arbitrary volume. Let's say we're going to go up, right? I have volume. I'm increasing the pressure. If I have a fixed volume and I'm increasing the pressure, the temperature must go up as well, right? Intuitively. So that's why your isotherms should end up looking something like that. This comes from PV is equal to nRT. All right. Okay. And then what we can do, we're asked for the heat and the work terms. Heat added to the gas and then work done by the gas. So right, change in internal energy is equal to any heat added to the system minus any work done by the system, okay? First law. So let's see where we can start. We're trying to get the area under this curve. So we have the isotherm, right? We're trying to get this area. That's one thing that we can think about. This is the work, right? Because if we remember, work is equal to volume 1, volume 2, dV, okay? Yeah. The integral from volume 1 to volume 2 of P dV, right? So it's working in this pressure field, right? It's working against some pressure, okay? And what we will do, we need to get this area under the curve, right? It's not an easy rectangle, but we can still do it, right? Because we're on this isotherm line, this integral becomes easier, right? So P is a function of V. You could also say P is a function of T as well, but T is isothermal. We'll see what happens. So just say, let's replace P with what we can get from ideal gas, right? So P is equal to nRT divided by V. N is equal to 1 in this case. So then we have RTV dV integral V1 to V2, right? So what we can do next is execute this integral. Because T is constant, T is equal to 300K, R is constant, V is the only thing that changes. Take these out of the integrand. We know this one. It's a classic one. We know this integral, 1 over V, is ln of V2 over V1, right? And then what we can do next, that's work, right? So that's 1. Let's calculate the number. We end up getting RT, so R we know, T we know, this is 300K. If you do this simplification, you end up getting ln of 5, right? Because if you have, let's just be explicit about it. If you have 5 times V1, this is V2 over V1, right? You're left with 5. This ends up being 4.01. Okay? Of work done by the gas, right? Because we're going from V1 to V2, right? Isothermal expansion. Small volume, bigger volume. And then what we can do is look back at our first law. We have isothermal. So we know W, so let's write W. Isothermal, that tells us some information. In an isothermal process for an ideal gas, du is equal to 0 for isothermal expansion of ideal gas. Why? Why? Because for an ideal gas, remember, for an ideal gas, change in internal energy is only proportional to change in temperature, right? That's for a simple ideal gas with non-interacting particles, right? If you have interacting particles, then you can have a change in internal energy without necessarily having a change in temperature. Even in those cases, temperature has, I believe it has the higher effect, but for an ideal gas, non-interacting particles, this holds true. That's why we can say if we have an isothermal process, I know that we didn't change our internal energy, because for an isothermal process for an ideal gas, temperature is just an indicator for internal energy. And again, that's just for this case of the ideal gas. Okay? So this was one of the answers too that was asked. Change in internal energy is equal to 0. So that means this is equal to 0. That means we know Q. So Q, or we can get Q. Q is equal to W. All right, just move Q over here, 0 here. So Q is equal to W, work. Heat is equal to work in this case. And work done by the gas was 4.01. Right? So this was heat added to the system. And then this was energy added to the system. This was energy leaving the system. Energy added to the system as heat. Energy leaving the system as work. Right? So this is isothermal expansion. So in this case, I won't do the piston. Here is state 1. Here's state 1, right? We'll call this state 2. Piston. Piston contracted, piston expanded, right? What we have here is to get from 1 to 2, we added heat and work was done by, so I don't want to do add. Heat goes in, work leaves, right, to expand the system. And it's when that's done equally, T is constant, okay, for an ideal gas, right? And this is just using our path here, okay? Okay, now we're going to do adiabatic reversible expansion, okay? Reversible adiabatic expansion. And let's write out what the problem gave us first. Small up here, because we have a lot to write this time. So I will say N is equal to 1 mole, right? Gamma, which is Cp over Cv, is equal to 5/3. We have V1 is equal to 2L. We have V2 is equal to 3L. And T1 is equal to 400K, right? Okay. So we need to calculate T2, and we need to calculate D, delta U, Q, and W, okay? So how can we do that? We don't know. So here's what I would think. I would think to get du, we need to do You should always think something along these lines. N CV delta T. But we don't know the final temperature, right? Okay. Let's draw the PV diagram, small, right? The PV diagram will look something like this. V, P. Remember, in a PV diagram, you have the isotherms, right? But for adiabatic expansion, you're not holding any of the state variables constant. So you don't have constant pressure, so you're not moving vertically. You don't have constant volume, so you're not moving, scratch that. You don't have constant pressure, so you're not moving horizontally. There you go. You don't have constant volume, so you're not moving vertically. And you don't have isotherms. You're not moving along these constant temperature isotherms, right? Let me put T. T high, T low. What you're doing instead, you're moving along these adiabatic, constant adiabatic, right? Adiabats, I believe they're called, right? I believe they should be a little steeper than the isotherms. And these come from the fact that you could say for an adiabatic process, P1 V1 raised to P1 times V1 raised to gamma is equal to P2 times V2 raised to gamma, right? We're going to derive that. And yeah, so I don't want to just say, for the test, yes, remember this. It should come to your head very quickly, right? But let's go through why that's the case. And I would also recommend, you never know, that sounds like a good test question. Can you derive this, right? Okay. So let's get started. du is equal to dq minus dw, right? Why am I doing the differential form? Because I want to just derive this. I'm not doing it for this problem. I'm just doing this in general, right? Okay, so for an adiabatic process, dq is 0. Okay? So du and dw, right? And I'm trying to get this in terms of ideal gas, you know, ideal gas-like things, right? So P, V, T. I'm trying to get it in terms of P, V, and T, right? What I have on this diagram, right? So how can I do that here? Well, immediately I think that I can do P, this differential, inexact differential, so forgive my D here. The inexact differential W is equal to this exact differential minus P times dV. And then this right here, du, think about an ideal gas, right? We've been saying this for a while. For an ideal gas, U is directly proportional to T, right? And they're only proportional to T, right? So in an ideal gas, there's no intermolecular interactions, right? So any change in T is a change in internal energy, or any internal energy change is a change in T, right? In other cases where there's interactions, right, the internal energy may increase without temperature necessarily increasing, right? So, but that is not the case for the ideal gas, right? So think U du for ideal gas. Well, we know that is CV dt. Let's assume 1 mole. So it's N, but let's assume I'm doing this for 1 mole, okay? For simplicity. Okay, so I have CV dt is equal to minus P dV, right? So this is good. I have T and I have V, which is what's on my diagram here, which I kind of want this in terms of. What's next? What should I do? Well, I can integrate both sides, but P, this is a problem, right? P here changes. This changes as a function of P. So P is not constant during this adiabatic process, right? So you see here, P does change, but how does it change? I know that this is an ideal gas. The equation of state is PV is equal to nRT. So P, I could just move the V down here, and I have P is equal to nRT over V. And N is equal to 1 in this case. Okay. RT dV over V. Okay. It's equal to CV dt. Yep. And then I can take T, right? So I can't do this, and T also changes, right? I can't do this integral just yet. T also changes. We see it's changing here. Harder to see, it's crossing these isotherms, meaning if this had a color dimension, you could see that T is changing. So, but I can move T to this side with the dt over here, right? So I can say CV divided by T, right? So T is not held constant in this adiabatic expansion. P is not held constant in this adiabatic expansion, right? So that's why I can't do this integral dV, right? I have to do it with dt. I'm going to do R. R is left over V dV. Okay? I know these integrals. You know these integrals. This will be from T1 to T2. And this will be from V1 to V2. Okay? And then what we will see is that we have CV ln T1 over T2 over T1 is equal to, let's see where we were. I'm missing a negative somewhere, I believe. Yeah, let's do the integral. I'm missing a negative somewhere. I believe I should have a negative somewhere in front of this. Let me find it. Ah, yeah, the negative's here. My bad, please forgive me. So the negative is here, and it will get carried down here. Right? Do we see the negative from the minus P dV should just follow, right? And then to get rid of this, because negatives are problematic, right? It's hard to carry them around. If you say the negative goes in here, you flip. Remember your logarithm rules. You can flip you can do the inverse of the argument in here, right? So that ends up being R ln V1 over V2 equal CV ln T2 T1, okay? And what is that? So this is good. We have things in terms of T's and V's, right? I have this CV here I don't love, right? So what can we do? Also the R. The R, this is fine. This can be a little fraught, right? So what I can do instead, remember your logarithm rules. In fact, I'll write the logarithm rule maybe down here. Let's say we have a ln x, that's equal to ln of x raised to the a. Okay, remember the log rule. That's a good one to know. I can do the same here. So this ends up being ln t2 t1. This is raised to CV. It's getting a little messy. I do the same here. R, right? Then I can take the exponential of both sides. That basically gets rid of this. So then I'm left with this up here, which is yeah, I don't need to look at the paper. It's right in front of me. This is CV is equal to V1, V2, R. Okay. That's good. It's not the final form. So what we can do, if I argument, exponent, exponent, if I were to say divide this exponent by CV, I have to divide this exponent by CV. Remember the exponent rules. These are important to know. This ends up being 1, and then recall that R is equal to CP minus CV, right? So then this can be written as CP, CV, CV and CV cancel, so minus 1. This is gamma, right? So we're close, right? And I think that's probably all we need for this problem. But you could continue and take this and get you to this form, right? So know that here we can get to here. But why am I stopping here? Well, what's nice about stopping here is that I have solved for T2. I know V1, V2, I know T1, I know gamma, and I know that this is 1, right? So that's fine. This is harder for me to remember, so I would probably start here and then work my way starting here. This is also good to remember. Honestly, try to remember them all, or you can derive it. I don't recommend deriving it on an exam. That seems fraught, right? But yes, so I did the derivation. Basically, this is how we can get this. Do you see how these are similar, right? It's a relationship between state 1 and state 2, right? We can continue to do this. We could continue to do this to have all the the state 1 terms on one side and state 2 terms on the other side, but this is sufficient, right? So what we can do, if we solve, we have T1, V1, V2, gamma. T2, if we do the math, ends up coming out to be 192 Kelvin, right? Now, let's go here and say, why is this temperature lower, right? Well, that makes sense. It's adiabatic expansion. So we have P, V. We know that V is increasing. If V increases, P will decrease, T will decrease, just looking at this sketch. You should always be able to sketch the surface of the ideal gas, right? So this is a 3D thing. This is 3D. We're just choosing P and V to look right at it, and then we're choosing T to be the isotherm, right? So we're saying in this area, T is high. In this area, T is low. And if you see here, then you could see why we decreased temperature, right? And the adiabatic goes down. Okay, so we have T2, and that's good. Now that we have T2, the rest becomes easy, right? So remember, we're dealing with an ideal gas. Ideal gas. Ideal gas is in an ideal gas, the change in internal energy is directly proportional to the change in temperature. These are directly related. So we have the change in temperature. So we can say du is equal to, it's 1 mole. So we will say CV, CV would be, I'm bad, I don't remember. Yeah, CV would be equal to, let's see, I have it written down. Yeah, 5 to R, right? And then you have delta T, right? So you have delta T, that was, where did you start? You started at that temperature, so it will be 1, can you see? Minus 400. It's low cutoff. 192 minus 400, this is a negative number. That's a negative delta T. This means that delta U ends up being, delta U will be, this is not the right one. Delta U will be, please be patient with me. I'm from the 1900s. All right, so, yeah, there it is, there it is, there it is. Yeah, negative 2.59 kilojoules. Okay, so that's your answer there, negative 2.59 kilojoules for delta U. It's a negative delta U, right? Ideal gas, temperature went down, so does du, change in U, okay? And one more, we were asked for work, so let's, where's our first law? Did I even write it for this one? I did most of the deriving, no. It's adiabatic. First law says, change in internal energy is equal to Q minus W. Heat input to the system minus work done by the system. There is no heat exchanged. So if the work, yeah, so if delta U is negative 2.59 kilojoules, work will be the opposite of that. It'll be 2.59 kilojoules, work done by the system. This is work done by the system. That's easy to know because I think the A&M logo might be blocking that, but work is, it's going to be equal to negative U, okay? I had lost my train of thought. There was, oh yeah, we have expansion, right? We have expansion, so work done by the system, right? So work is being done to expand the system. All right, we have one more. Okay, here's an interesting one. So we're trying to find surface work, okay? So we are told that we have a thin film, we have a surface tension, and we need to figure out how much work is done to expand this film, okay? So let me draw a picture first, because this is a little difficult, right, I would say. I have a film, extremely thin film. Okay. On one side, I have air. Here, I have film. And then there, I have more film, right? Okay. I want to expand this film. So let's see what the best way to do it is. A1, and I want to expand it. Let me change the color. I want to basically pull and expand this out. Ooh, maybe I go back to blue. And I want to add this area. This is like A2. Both of it's A2, right? So I want to expand, right? So to do that, there's some energy cost, right? There's some work required to do that, to expand from A1 to A2, right? Or you could think of it like this as well, where you have, and you're pulling, right? There's surface tension, okay? What is surface tension, right? Surface tension is the equivalent of pressure, but in 2D. And there's also something called line tension, right, in 1D. It's the energy cost to expand the system, right? In 3D, that's a volume. In 2D, that is a surface energy, surface tension, rather. Okay. So let's draw a PV diagram, or not a PV, PVX, right? It's not PV. Surface tension area, right? It's important to know that in this case, we're just going to assume that surface tension does not vary in any way with area, right? So it's constant. So what we can say then is if surface tension is constant, we expand the area, then it's just the area under this curve. So work should be, surface work would be the integral from area 1 to area 2 surface tension dA, right? Wrong. That is because we have two surfaces, unfortunately. We have the surface on this end and this end. So why is that weird, right? You could have situations where you're just introducing one surface, right? A situation where you're introducing one surface is nucleation, and you'll learn about that in kinetics, I'm sure. But if I wanted to say introduce one surface, so here is the initial state, nothing in it. Here is the final state. Let me see if this fits. A droplet has formed. I introduced one surface, right? There's only one interface, right? And it's this circle. I have two. Do you see? It's a film, not a sphere, right? If it were closed, it's, ooh, that's hard to say. A droplet, right? I introduced one surface. There's two here, okay? You just needed two, okay? I left off the surface tension here, but that can be evaluated. I believe it is 1.2 times 10 to the negative 4 joules to create this surface. And if you want more information on this, something that I thought was really cool when I was a student was the Texas A&M Physics Festivals. They have a really, really good demonstration of surface energy, surface tension, and the work required to expand a surface. So I recommend maybe Googling bubble surface tension experiment, right? If you want an intuitive view of this. That's just my 2 cents for that.